Hello students, I welcome you all for the online lecture series of design of steel structure. In today's lecture, we are going to learn the numerical on laterally supported beam subjected to the high shear and the bending moment. So, following is the statement of our numerical. Check whether ISLB 350 about 49.5 kg per meter laterally supported throughout the span of 6 meter for the following data. The maximum factored bending moment is 180 kN meter. The maximum shear force is 210 kN. The grade of the steel is Fe410. Following is the diagram of our I section. The step number 1 is to write down the given data. According to the given data, span L is equals to 600 mm. Mu, that is maximum bending moment, is 140 kN meter. A small correction, student. The maximum bending moment is 140 kN meter. Vu is 210 kN. Fu is 410 MPa. Fy is 250 MPa. And gamma m0 is 1.1. Then we have to write down the properties of ISLB 350 about 49.5 kg per meter. Following are the properties which are written from the steel table. H, total depth 350 mm. Bf, width of the flange 165 mm. Tf, thickness of the flange 11.4 mm. Tw, thickness of the web 7.4 mm. Ixx, that is Izz, is equals to 13,158.3 into 10 raised to 4 mm raised to 4. H1, that is the depth of the flange, is equals to 288.3 mm. Zp of the section is 851.11 into 10 raised to 3 mm cube. Ze is 751.9 into 10 raised to 3 mm cube. R1 is 16 mm. Student, I am always noting you that always look in the conversion of the unit. All the values are in mm, MPa. That's why you need to convert the moment shear force in the Newton only. Then our second step is to classify the cross section. According to the table number 2 of IS 800 2007, we have to classify the section. Flange criteria. Flange criteria Bf upon Tf. Here Bf is equals to Bf by 2 upon Tf. Here Bf is equals to 165 mm and divided by 2, and the whole is divided by Tf, and hence our value of flange criteria is 7.23 and it is less than 9.4 epsilon. Hence our flange is plastic. Then wave of the section H1 upon Tw, as this value is 38.95, it is less than 84 epsilon. Hence our wave is also plastic. As our flange is plastic, wave is plastic, therefore our section is plastic, and hence our value of beta b is equals to 1. Then the next step is to calculate the design shear strength of the section. Clause number 8.4.1 of page number 59 gives us the formula for the design shear strength of the section. Vd is equals to Fyw into Aw divided by root 3 gamma m0. So substituting the values into the given formula, we get Vd is equals to 339.84 kilonewton, which is greater than Vu. Then we have to check the beam for the high or low shear condition, which is equals to 0.6 Vd. It should be greater than Vu. If it is greater than Vu, it is a case of low shear. But in this case, 0.6 Vd is less than Vu, hence it is a case of high shear. Note that whenever it is a case of high shear, we have different formula to calculate the bending strength. So the design bending strength for the high shear condition is calculated from clause number 8.2.1.4, page number 53. So for the plastic and compact section, we have the formula for MD is equals to MdV, which is equals to MD minus beta into bracket MD minus MFD, and this value should be less than or equals to 1.2 ZeFy divided by gamma m0. Then we have to calculate the MFD first. As value of MD we have calculated, then MFD is equals to ZFD into Fy divided by gamma m0, and ZFD is equals to AF into bracket H minus TF into Fy divided by gamma m0. AF is 165 mm into 114. AF means area of the flange. 165, that is the BF into thickness of flange, and that is TF into bracket H minus TF, that is the total depth minus thickness of the flange, and divided by 1.1, that is the value of gamma m0. We get the value of MFD as 144.75 kilonewton meter. Then we calculate the beta MD, which is equals to beta B into ZP into Fy divided by gamma m0, and hence value of MD is equals to, as beta B is 1, ZP is equals to 851.11 raised to into 10 raised to 3 into Fy is 250 MPa divided by gamma m0 is 1.1. Again the same thing. Look the unit of ZP. It should be in the mm cube, as the value of Fy is in Newton per mm square, MPa. Then MD is equals to 193.43 kilonewton meter. Then beta is equals to, there is difference in between beta B and beta. Here beta is equals to 2 into Vu divided by Vd minus 1 bracket square, and hence substituting the relative values into the formula, we get beta is equals to 0.055. Substituting all this value into our formula, we get the value of MD is equals to, that is MDV is equals to 190.75 kilonewton meter, and it is less than 1.2 ZE into Fy divided by gamma m0, and greater than mu, that is 180 kilonewton meter. Hence the next step, our next step is to calculate the check of web buckling. So FWB is equals to B into TW into FCD. Here we assume our bearing length as 150 mm. Then capital B is equals to 120 plus H1 upon 2, and hence we get the value of capital B as 294.15 mm for the end reaction. TW is 7.4 mm. So FCD depends upon the slenderness ratio lambda, which is equals to 2.45 into bracket H1 upon TW, and hence it is 95.45. We are assuming it approximately equals to 95. Then from the table number 9C, page number 42, and Fy is equals to 250 MPa, our value of FCD is equals to 114 MPa. Substituting the value of FWB, which is equals to B into TW into FCD. And hence we substitute in the values into this numerical formula, we get the result as FWB is equals to 248.14 kilonewton, and it is greater than VU, which is equals to 210 kilonewton. Hence our beam is safe for web buckling. Then the next check is the check for the web crippling. FW is equals to AE into FYW divided by gamma M0. FYW is equals to 250 MPa. Therefore, AE is equals to B1 into TW, which is equals to small b plus N1 into TW for the end reaction. Substituting the relative values, that is N1 is equals to TF plus 2.5 into TF plus R1, and TW's value is 7.4. We get the AE as 1616.9 mm square. Therefore, value of FW, that is the web crippling value, is equals to AE into FYW divided by gamma M0. We get FW is equals to 367.47 kilonewton, which is greater than VU, that is 210 kilonewton. And lastly, we can conclude that therefore our section ISLB 350 about 49.5 kilonewton per meter is safe to take the given moment and the shear force with the check of wave buckling and wave crippling. Thank you for watching the video. In next lecture we will be solving the numerical on next topic. Keep watching and subscribe the channel. Thank you.